Hello again. In the third part of this lesson on Chapter 11, I'd like to give you some tips about whether to use substitution or elimination, and then we'll talk about what to do if you have three variables and tackle an especially thorny story problem. First off, substitution or elimination. This system on the left, I'm looking for a feature of the system that I could exploit to make one or the other method easier. In this case, one method that would be very easy is if I solve this equation for this variable, this y here, I'm not going to have any fractions. I can just add 4x and get y equals 4x plus 17. Then in the other equation, I have 31x minus 6 times 4x plus 17 equals 2. Remember to distribute. 6 times 17 is 102? Yeah, 102. So 31x minus 24x is 7x, and add 102 to both sides, you get 104. Now, unfortunately, 104 is not divisible by 7, so you're going to get x is 104/7. And then when you substitute that back in, you're going to have problems. But at least the first part was clean. Over here on the right, what I'm noticing that should make this really easy for one or the other method is elimination here. 14 is a multiple of 7. So rather than having to say, if I tried to eliminate the y's, I would have to multiply the top by 13 and the bottom by 9. And then we would have real big numbers. But if I multiply the bottom by 2, I get 14x minus 26y equals 178. That's a lot nicer to work with. So then I can subtract the bottom line from the top line, and I get 9 minus 26 is negative 35. And 31 minus 178 is 147. Negative 147. So now all I need to do is divide both sides by 35. Nice thing is these both have a factor of negative 7, so the top becomes 21 and the bottom becomes 5. And it's not super pretty, but that's a lot easier than the first step would have been in substitution, or if I had tried to eliminate the y's. Now all I need to do is plug this number, the number I just got, 21/5, back into either equation for y and find out what x is. So those are some tips you can use to decide whether to use substitution or elimination. I'd like to briefly discuss what happens if we have three variables. Well, if you have three variables, you need three equations. For example, a problem could look like, oh boy, here we go. 2x plus 3y plus 4z equals negative 3. 5x plus 0y minus 1z equals 19. And 5x minus 2y plus 6z equals 36. Each one of these is the equation for a flat sheet in a three-dimensional room, and you're trying to decide how many intersections they have. The answers that are possible are still 0, 1, or infinity, but the thing gets a little harder to visualize. Now, I want to show you what you should do to start this problem. We can still use either substitution or elimination. If I'm using substitution, I'm going to pick the easiest equation to solve. Now that line in the middle, it has a 0 in it, which first off is going to make this a lot easier on us. And second, the z only has a factor of 1 on it, so I could write negative z equals 19 minus 5y, so z equals 5y minus 19. Now if I plug that into each of the other equations, think of it as I've already used the information in line 2 here, so now I'm going to apply that information to lines 1 and 3 to see what happens. So instead of writing 2x plus 3y plus 4z equals -3, I have 2x plus 3y plus 4 copies of 5y minus 19 equals -3. And in line 3, I have 5x minus 2y plus 6 copies of 5y minus 19 equals 36. What we've got right here, if I distribute the 4, combine like terms, distribute the 6, combine like terms, this is just a 2x2 system of equations, 2 equations, 2 variables, and so we solve this with one of the methods we already have. Otherwise, I could do elimination as well. Let's see, how would elimination look? Well, again, my goal is going to try to be to get a system of 2 equations and 2 variables, but this time it's going to take a little bit of elbow grease to do that. Line 2 and line 3, if I'm seeing them correctly, they both have a 5x in them, here and here. So these coefficients are already matched. Let's see what happens if I eliminate the x. I'm going to do line 3 and subtract line 2 from it. So that's going to be 5x plus 0y plus, undo, minus z equals 19. And from that, I'm going to subtract 5x minus 2y plus 6z equals 36. Oops. Well, I guess that's the order I'm doing these in now. That was, in fact, line 2 minus line 3, wasn't it? So, 5x minus 5x, that's a 0, just as we expected. 0y minus -2y is 2y. This will be minus 7z, and 19 minus 36 gets us a -17. So this is an equation with no x's in it now, just y's and z's. So I've used line 2 and line 3, I've used one pair, and now I need another pair of lines. I could do 1 and 3 or 1 and 2. Whichever one I pick, though, I'm going to try to eliminate x again. Let's do 1 and 2. Again, it's completely up to you, but I'm going to choose 1 and 2. So line 1 has a 2x in it. So I'm going to multiply it by 5. 2x times 5 is 10x, 3y times 5 is 15y, 4z times 5 is 20z. And that equals -15. So this is 5 times line 1. And now line 2 has a 5x in it. So I'm going to multiply it by 2 to get 10x. 0y times 2 is still 0y. Oh, not z. And -1z times 2 is -2z. On the right side, we have 38. And now if I subtract 2 of line 2 from 5 of line 1, so I'm subtracting here, once again, the x's will disappear. 20 minus -2 is 20 minus -2 is 22z. -15 minus 38 is -53. So now what I've got are this line, line 2 minus line 3, and here, 5 of line 1 minus 2 of line 2. These are both equations in terms of only y and z. So once again, I've eliminated x twice, so I've got 2 equations in 2 variables, and you have to pick 2 different pairs of equations here so that these are made of independent information. But now all I do is solve the 2x2. And you can solve, so you can start in either one of these ways. And look, here we got a 2x2 made of x and y. Here we got a 2x2 made of y and z. Either one of these is perfectly fine, though. Doesn't matter which one you pick. To finish off the problem, we solve one of these 2x2s. I'm going to go ahead and solve the one I got by elimination. So I have 2y minus 7z equals -17. and of 15y plus 22z equals negative 53. Sadly, it doesn't look like there's going to be a great way to solve this. I'll go ahead and use elimination. I usually prefer elimination, but it's up to you which one you like. I'll multiply the top line by 15 and the bottom line by 2 in order to get rid of y. So 15 times 2 is 30y. Oops, shouldn't put an equal sign there. These are two different equations. 30y minus, 15 times 7, 105z. 17 times 15, that's 255. But it should be negative. Okay. Wow, big numbers. And in this second line, I've got 2 times 15y, once again 30y, so I'll subtract to make those disappear, plus 44z equals negative 106. And now we subtract, the y's go away. Negative 105 minus 44, boy howdy, that's a big number. That'll be 149 copies of z. And as a great, wonderful coincidence, 255 minus 106, we get negative 149 over here. Oh, this should also be negative. So I divide both sides by 149, z equals 1. Now I'm going to take that and stick it back into either one of these equations. How about 15y plus 22 times 1 equals negative 53. So if I subtract 22 from both sides, I have 15y equals negative 53 minus 22 is negative 75. Divide both sides by 15, and we get that y equals negative 5. And now what I need to do, remember our original line 1 was something like 2x plus 3y plus 4z equals negative 3. If I take these two solutions, here and here, and plop them both in, this looks like 2x plus 3, y is negative 5, plus 4 times z is 1, equals negative 3. Now I just need to simplify, combine like terms. I'm going to add the 11 to each side. That'll be 2x equals 8, so x equals 4. And so my final answer is x, y, z equals 4, negative 5, 1. 4, negative 5, and 1. So that's how we solve a 3 by 3. We break it down into a 2 by 2 with either of our two methods. And then we solve that 2 by 2 using the way we already know. And you can check your work by saying, all right, my solution was 4, negative 5, 1. So in the first line, that says 8 minus 15 plus 4, that is negative 3. 20 plus 0 minus 1, that's 19. 20 plus 10 plus 6, that's 36. So this point satisfies all three equations simultaneously. And that's what you do with three variables. With all elimination, all substitution, or even a mix of the two. You have a ton of choices. Just pick whichever one's going to be easiest for you. Finally, there's a tricky kind of problem that always shows up on the final. I'd like to make sure you're prepared for it. It's called a mixture problem. Let's say that I have two cauldrons of boiling metal. And I'm going to be forging steel. Now, cauldron 1 contains 18% nickel and 82% iron. Cauldron 2 contains a mixture of 12% nickel, not mickle, nickel, and the other 88% is iron. An order comes down the line. One of the companies that we're a vendor for says, we want 400 kilograms, please, in bars of steel with a 13% nickel content. Now, this metal is expensive, and once it's mixed, you can't unmix it. So what I'm trying to do is, this is what I've got hot, this is a rush order. I'm going to want to mix a lot of this, a lot of Cauldron 2, with a little bit of Cauldron 1, so that the final concentration of nickel is exactly 13%. How in the world do I do that, I hear you asking? Well, it's really just a system of equations. Let's say we use X kilograms from Cauldron 1 and Y kilograms from Cauldron 2. Can we come up with some equations involving X and Y? We sure can. First off, I know that X plus Y has to be 400. This is the total mass. Almost every mixture problem is going to have one equation for total mass, and that'll be the easy one to set up. So the mass of the metal we take from Cauldron 1 plus the mass of the metal we take from Cauldron 2 altogether must be 400 kilograms, because that's how much the customer ordered. And if I use any more than that, the boss is going to be mad at me for wasting material. So I want exactly 400. Now, they gave us two conditions. It doesn't really look like it, but they told us 400 kilograms, and they told us that the steel was 13% nickel. So what I can do is I can say, altogether, how much nickel has to be in the final cauldron? There's 400 kilograms, and it's 13% nickel. 400 times 0.13, put on my thinking cap for a second, that's 52 kilograms of nickel. This second equation is always going to be something to do with one of the subparts of your problem. That's why it's called a mixture problem. In this case, it's going to be the mass of the nickel. In the 400 kilograms of metal that the customer orders, they want 52 of those kilograms to be nickel, because that's 13%. So on the right-hand side here, I will put 52. Now, how do I specify how much nickel I'm mixing? Well, from Cauldron 1, 18% of the metal that comes out of Cauldron 1 is nickel. So I will have 0.18x kilograms of nickel sourced from Cauldron 1. And in the same way, I will have 0.12 times y kilograms of nickel sourced from Cauldron 2, because Cauldron 2 is 12% nickel. So my goal is to get 18% of the mass I take from Cauldron 1 plus 12% of the mass I take from Cauldron 2 to equal exactly the 52 kilograms of nickel I need, so that the customer gets the alloy they want. So then, this is my system of equations. And the good news is that we were able to make a system of equations. The bad news is that it is a pain. So I can use substitution. If I use substitution, solving for this x or this y would be very expedient. I could also use elimination, and I think that's what I'm going to do. Like I said, personally, I prefer elimination, but if you like substitution better, that's fine too. Solve one of these for x or y, plug it in, and you should be able to solve your equation. Me, I'm going to multiply this top line by 0.12 on both sides to eliminate y. So it'll look like 0.12x plus 0.12y equals, well, what's 400 times 0.12? It's 48. And now if I subtract, I get 0.06x plus 0 equals 4. Divide both sides by 0.06, x is 4 over 0.06, and that turns out to be the quantity 66.6 repeating kilograms. That's how much comes from Cauldron 1. I can plug that back into any other equation, but I definitely like to use line 1 up here, because that's the simplest. So now I know 66.6 bar plus y equals 400. Subtract the 66.6 from both sides, so y must equal 333.3 repeating kilograms. And now I can write my solution x comma y equals 66.6 repeating, comma 333.3 repeating. But this is a story problem, so it would be better if I wrote my solution in terms of the story, like this. Pour 66 kilograms from cauldron 1, and 333 kilograms from cauldron 2. So it's still a system of linear equations. It's just that the trick is setting these things up. Now, you'll have a few of these in your homework and some more on the study guide for the final. Do contact me if you're having trouble setting them up, and I'll be happy to help. Well, that's all for Chapter 11. Thanks for coming.